finished. Okay, so here, let's just talk about this on this number 35, the flux integrals. We'll talk about number 2 and number 4. So number 2 is similar to what we did in class. So before this has, what, 6 sides to it? The cube will have 6 sides. But for every side, you can use the n.ds way of doing flux, right? So you can do the integral of f dot n ds. And if your surface is parallel to one of the coordinate planes, then ds just is the same as dA, which is either dy dx, dy dz, dx dz. So that was the situation that I recommended that you use this form in, was if your surface is parallel to one of the coordinate planes. And if that's the case, then ds is just dA. It's just either whatever plane you're parallel to, dy dx, dy dz, dx dz, one of those. And then you determine your n vector, in this case for outward orientation, and you do the dot product with the field. So can you kind of maybe tell me why the success rate on this was a little bit lower? Was there something tricky about it, or can you? Yeah.
I think something that confused me is that if I remember correctly, you don't do the dot product with the field that's given there. You have to put in whatever, like it's x and y there. You have to put those in according to the position, like what that is for the cube.
Yeah, so that will always be true. So you always have to rewrite your field in terms of the 2 variables. So that
I think at first I got confused. I looked at that and like, oh, you just dot that f thing and give it there, but you never do that.
Well, no. So you'll keep it 4x, 4y for the top and the bottom. For the top and the bottom, that's when you have the variables x and y. But like for the front and the back, so you have like the front is going to be what, x equals 3. So then you're going to plug x equals 3 in, and then your variables are y and z. And then for the back of it, you have x equals 0. So for every point on that thing, x is 0. So you can plug 0 into the field. Yeah. So and that's true for line integrals, surface integrals. You'll always rewrite that vector field in terms of the parameterization of your surface. So you have the same variables there as you do that you're doing it with. Okay, other questions or maybe insights onto why this was hard to get the right answer? Because I think it's probably pretty straightforward, like the example we did in class. So, are we good? Can you take it from there? Yes, please.
I think one of your YouTube videos is playing, like as you're talking right now.
Can you hear it?
Yeah. Oh yeah, it even has a sound icon.
Is it gone now?
It was like going crazy.
Is it gone now? Okay.
That's one of the largest recorded cases of collective schizophrenia.
Okay.
I have a question.
That's not the worst thing that could have happened. Yeah.
I saw a note on 34 that all you had to do was 8 problems.
Yeah.
Is that true? Okay. Just making sure.
No, just kidding. You got to do them all. No, yeah, yes. So if you got 8 of those, because we didn't do any examples of those. I told you, that was kind of a residual. It was kind of a residual effect of finding the flux integral. It's just what just ds, right? Right, and ds was magnitude. My pen ran out of ink. Yep, so I gave you the formula, but we didn't do any examples. So for that reason, I just said if you can find 8 that you can do, that's full credit, okay? Other questions? Those are important, but and that's a great application of this, is that you can actually find areas of surfaces, right? But we just didn't take the time to do any examples. Okay, so the other one that was this kind of conceptual problem, number 4, had a little bit lower success, and maybe that's because I gave you less tries. Let's see that one. That's the one. No, this one. No. Anyway, I think it's 4. So is the flux positive, negative, or 0? So this one. Positive, negative, or 0? And why is this one, why does this have a 0 flux?
The flow is always parallel to the surface.
Okay. So what does that mean point-wise? Point-wise on the surface. What about the flux?
There's no variable component of flux each point, or orthogonal.
Okay. Therefore, what is it? Point-wise on the surface, the flux is? At every single point on the surface, the flux is 0. There's no flow through the surface. It's all parallel to the surface. So for that reason, the flux is 0. What about this one? Stop. All right, on the left side over here, the right side? Positive, because so you have an amount of flow outward. It's outward orientation. So you got positive flux on the left side. But then on the right side, it's positive because it's outward. But on the left side over here, equal and opposite to that. So for that reason, it's 0 because you have the amount going in is the same as the amount going out, or the rate coming in is the same as the rate coming out. So the net effect is 0 for the whole surface. So they're both 0, but for different reasons. Okay. So please use the email instructor button. Bring these questions to office hours. We're working through if you're having difficulty with examples. There's just not enough time to do every type of example in class. I mean, in fact, there's only time in class to do 1 or 2 examples. So, and that's just the nature of it. So get the help outside of class that you need. I'm willing to take the time to do that. All right. So let's finish that example from last time. I posted on the video, but we have time to actually finish that example from last time, which was, no, this one. So I think we did this was the closed surface, which was the cone and the disk. We wanted outward orientation. And I think we finished, so S1 was the cone, S2 is the disk. I think we finished S1 last time, is that right? We set it up, and so let's just set it up again. What was it?
So a vector r sine theta.
So this is r sine theta, negative r cos theta, r.
Dot r cosine theta, r sine theta, negative.
Yeah, we wanted to pick the orientation that had a negative z value for outward orientation, right? The vectors are orthogonal to this cone, point downish. So outward orientation means z is less than 0, right? Z is less than 0. So it was r cos, r sine theta, negative r. And then we said, because the whole time we were, our the variables that we're using, u and v, were r and theta, it's just going to be dr d theta. We're not making a transformation from rectangular coordinates into polar. We just started with polar. So it's not going to be r dr d theta, just dr d theta, because that's our du dv. And then, did I tell you what the answer was? I think it's 192 pi over 3, if I remember right. Okay, so then S2. S2 is the disk at z equals 4. So first we need to parameterize that. So for a disk at z equals 4, so what will my 2 parameters be to get all the points on that disk? What parameters will I use to get every point on that disk? R and theta again, right? Because we can have any distance from, we want the points any distance from the z-axis, and then at any theta. That will again give us, and now we'll have r cos theta, r sine theta, and z is always 4. Okay, how do we want to approach this surface integral? Always take the path of least resistance. So what do we want to do for this one? Do we want to write, so we have our general form of the cross product, we have the f dot n, and then we have, if you parameterize in x and y, we have that general case with the p, q, and r. So which of those three makes sense here? What's that? Because that has to do with mathematical efficiency. You always want, if you have choices in mathematics, pick the most efficient one. Yeah. So, and it's a matter of recognizing what's going to be most efficient. You know. So, why do a solution that has 8 steps when there's a more elegant solution with 3 steps? That's what I mean by that. So, what's the most elegant way to solve this? What's that? F dot n, right? F dot n, because our surface is parallel to the xy plane. So we use the F dot n, for sure. Okay, and so we're going to write F in terms of, so what's y is r sine theta, negative x, and z. So that's my f, right? Written in terms of our 2 variables r and theta. Dot n, what is n? For outward orientation. 0, 0, 1. And then? Yeah, but okay, so hold the phone a little bit though here. X, so this is y, negative x, and z, right? And then this is what, x, y, and z for this. So we're really in Cartesian coordinates here. So I am here, I'm taking y, negative x, and z, and I am doing a transformation into r and theta. Right, so I should have started with this, and then we're writing that. So this now is when we're going to need the r dr d theta. Because really this is, we're doing this in terms of x, y, and z. But then we're changing those x, y, and z into r and theta. So then this dx dy is going to have the r dr d theta. Okay, does that make sense?
So I'm assuming you would want to convert, say, n into polar just because it'd be harder.
Well, it's I don't think you can, right? So you can't because that's a third variable. All right, so then we have what, 4? So the dot product is 4, so we got 4r dr d theta. And then r is going to go from 0 to 4, and theta 0 to 2 pi. So what's this going to give us? 2r squared from 0 to 4. Is that 32? 64 pi? And so, so if I now remember correct, this is negative. Okay. So then, what is the total flux? No, it's not 0. Well, this is wrong. What is that? Okay, let's see. $128. Is that what it is? That's 2/3 of this. That's half. So then I think this is right. We're going to find out later in class. So I think it's this, which is so what's 192 minus 128? Is that another 64? So is it 64 pi over 3? I'm pretty sure that's right. But so whatever this is some negative value. This is 64 pi. You're going to add these two together to get the outward flux, right? The outward flux. And if I remember correctly, I don't want to take the time to do all the math. So if I remember correctly, it's 64 pi over 3. But like I said, later in class, we're going to confirm that. Okay, questions on setting up the flux of this closed surface? S1 or S2? Is it okay? All right, so we're going to talk about something now called flux density. Flux density. What is flux density? So flux density is the rate of change of flow of vector field out from a given point of the field. The rate of change of flow of a vector field out from a given point in the field. So here's a formula for that. Looks a little scary at first, but it's not too bad. So flux density, so we're going to take a small closed surface around the point and find the flux out of that. And then we're going to divide that by how much volume is inside. That's the density part of it, right? And then we're going to let that volume shrink down to a point. So it's the flux per volume, right? It's the flux coming out per volume, but then limited down to a single point. So mathematically, then what's the flux through the closed surface? That's just our flux f dot ds, right? Double integral, surface integral, divided by the volume within S. But then looking at that limit as it gets small down to a point. So if you have a lot of flux for a really small volume, that's a high flux density, right? If you have a very low flux for a big volume, it's a low flux density. So it's like how much flux per volume. Does that make sense? So that's the general formula then. This flux density is, in general, it's flux per volume. But again, volume shrunk down to the limit of that as the volume shrinks down to just like a point volume. Okay, so this is a nice defining example here. So if you have the field is XYZ, so what is that? A radial field outward. And the magnitude of any vector is the same as its distance from the origin. Right, so the magnitude of xyz is always going to be the same as how far it is away, because that's the coordinates of the initial point, right? So if you take a sphere of radius a, then the magnitude of this orange vector is the magnitude of that orange vector, if it's a vector at the sphere of radius a. So this is the point xyz right here, which is radius a, so that's like the length from there to there. But then the vector is xyz. So what's the magnitude of that vector? A. You see, it's just A. You see that? Because that length of that radius will be the same as the length of the vector, right? Because it's a radial. It's a field that the vectors grow as you move away, and the size of the vector is just how far you are away from the origin. Okay, so we're going to calculate the flux density at the origin. So remember, flux was F dot S, and we could use this, the F S cosine theta, magnitude of F. What was the magnitude of F? What's the magnitude of our orange vector? A, right? A, the radius of the sphere that it's sitting on. What's the magnitude of S? Magnitude of S would be the area, so it'd be the surface area of the sphere. And then what would cosine theta be?
The angle between
Angle between,
the orthogonal vector to the surface
right.
and the flow vector.
So what will cosine theta be? 1, right? Because that's in the direction, right? This vector is in the direction of orthogonal to the surface. So that'll just be 1. So then we get the flux is, it would be A times 4 pi A squared, which is the little area of the sphere. Theta equals 0 because cosine 1. So the flux is 4 pi A cubed. And so that'll be true for any size sphere, right? It'll be true for big spheres and smaller spheres. So that the limit, as you bring it down to a point, is still the 4 pi A cubed. Because that flux will be the same flux no matter what size sphere you have. So then the flux density is the limit of the flux, the 4 pi A cubed, divided by volume. The volume of our sphere is 4/3 pi A cubed. And then you get 3. So this is irregardless of the radius. And so then you get a flux of 3 at the origin. Flux density of 3 at the origin.
Would the flux density be
I'm not sure, but this calculates it for the origin. It gets a lot more complicated if your point is in the origin, because you have all this symmetry at the origin, right? That we could say that the magnitude of the vector was the same as A, right? As soon as you move away from the origin, that's all off the table. Okay, but when I read this definition of flux density, the rate of change of flow out from a given point, did that remind you of anything? Did you think anything when I read that? What did we say divergence was?
Is it like how much, like a field is expanding at any point?
Right, but remember it was the rate of change of the field. It was the rate of change in terms of expansion, and it was pointwise, right? So it was the rate of change of a field pointwise in terms of expansion rate of change. Is that kind of what that says? So what is the divergence of this field? What is the divergence of this field? What is the divergence of F? It's the partial with respect to x plus the partial with respect to y plus the partial with respect to z, which is 3. See? If you do, that's 1 plus 1 plus 1. Partial with respect to x, partial with respect to y, partial with respect to z. Add them up, you get 3. Lo and behold, we're getting the same value. Okay, so this is not a proof, but it certainly seems like good evidence that flux density is the same as divergence, okay? And I'll tell you that it is, but this isn't a proof, right? This is just using a really easy example to show that they're the same, right? To show that flux density and divergence are the same for this very simple defining example. Okay, questions on flux density. So now I'm going to give you an outline of the actual proof. Or a proof of what's called the divergence theorem. Questions? Okay, so here is, we have a solid E with a closed boundary S in a vector field F. Okay, so we've done lots of problems like this now. Closed surface, S, which is enclosing about a solid E. So you take one element as like a box, right? So of all that whole thing, we're going to partition it. A three-dimensional partition means one of those elements is like a box. Okay, so here's the box, and then at the box we have some P, Q, and R. But then, like we've seen before, like on this, given little changes, you have the vector field vectors kind of around the box, which could be slightly altered depending on the change that you have. For instance, here's for a change of x, you may have p x naught y naught z naught on the one side, but then you have p of x naught plus delta x y naught z naught. So your p vector is slightly different across the change in x in the field. So this is the P component of the field, and then for a change in x, here's the new P component of the field, slightly different according to the change in the x coordinate. Okay, so then the flux density, we want to calculate the flux density at this point, right, where this element is at this point. And so what that's going to be the flux through the cube over the volume of the cube as the volume goes to 0, right? That's what our definition for flux density was. So here's how we're going to compute that. So we're going to have three components of that, right? Three components of the flux according to x and y and z. And so the component of the flux in the x direction is going to be the change in the p component. Right, so how do we calculate flux? Flux is vector, the area vector times, or the area times the vector of flow, right? The magnitude of the vector. So so across delta x, we have the change in p, right? This p final minus p initial. So that orange vector, how much the change in p is like the difference of those two orange vectors times the area, right? Delta y, delta z is that area face. So flux is the magnitude of the vector times the area. And we can do that 3 times, right? You're going to do that for an xz plane, and the yz plane, and the xy plane. And that divided by the volume of the cube, which is just delta x, delta y, delta z. So I'm summing up those 3 to get the flux, dividing by the volume, calculating flux density here. And so what I can do is then I can split up that fraction into 3 fractions. And then you see this first one. In the first fraction, delta y and delta z cancel out, and we have the change in p over delta x. Similar will happen here. You have the change in q over delta y, and then the change in r over delta z. Well, those are just the partial derivatives of p with respect to x, q with respect to y, r with respect to z. And what's that right there? The divergence. So this is a proof. This is a proof that flux density is the same as divergence. by looking at one element. Okay, so now if divergence of F, if that equals what? Flux density, which is flux over volume, then what would flux equal? What would flux equal? Essentially, flux would be flux density times volume, right? So if I could just rearrange that, multiply both sides by volume. So the flux out of one box, is the divergence, the flux density, times the volume of the box. That's just, all I'm doing is just multiplying both sides by the volume of the box, right? So the flux out of one box is the divergence, which we know is flux density. That was flux per volume, so times volume is going to give you flux. So we're going to use that to prove something called the divergence theorem. So this is going to be for the next screen. But this screen shows how flux density and divergence of F are one and the same. This is a proof now. Okay, so the divergence theorem. The divergence theorem, we're gonna calculate the sum of the flux out of all the elements, right? So that thing is just a bunch of elements that are comprising the E solid, and I'm going to sum up all the flux out of all those elements, out of all those delta V boxes. And I'm going to do it two ways. The way I just said, right? So what was the flux? The flux is the divergence times the volume. We just said that, right? I'm going to sum that up for all the boxes. So that's kind of like the direct way of doing it. From the last screen, we said this was flux. So the flux out of all the boxes is the sum of the flux out of all the boxes. It's just flux as the divergence at every point times the volume of that little element at that point. Okay, the other way I'm going to do this is I'm going to think about all these boxes adjacent to one another. And as I calculate the flux, say, out of this box, and add those together, what's going to happen? We've seen this principle before. What's that? Yeah, like for these two, do you see that the flux on that side, the right side of that one, will be equal and opposite to the flux on the left side of that one? And those will cancel out. Yeah, we saw this in Green's theorem. And then the back side of this one will cancel out with the front side of this one. They'll be equal and opposite flux. So what will happen then? When all those cancellations take place, then what will the sum of the flux out of all the delta V boxes be? Yeah, it'll be the flux out of S. Do you see that? Because all the interior sides will share a face and have equal and opposite. That flux will cancel out. And so when you sum them all up, you'll get what? The flux out of S. Well, what's that? The flux out of S is, how do we calculate that? Nothing to do with divergence. That's what we've been doing, right? Calculating the flux out of a closed surface. Surface integral, right? So the sum of the surface integrals for all the boxes is just going to be, you're going to have that canceling effect on all the shared sides. And what's left is, that don't have shared sides, is S, right? It's going to be the flux out of S, the boundary of the whole thing. So summing up the flux as each flux has divergence times delta V is taking the triple integral across E. So point-wise, for all the points within E, you're going to calculate divergence of F dV. this way is the surface integral of the totally of the outside. And because those are both calculating the sum of the flux out of all the little elements, they're equal. So for the divergence theorem says if E is a solid with a piecewise smooth boundary S, if F is a smooth vector field defined everywhere in E and on S, then you have this. That the surface integral of the boundary is equal to the sum of all the flux coming out of every point throughout the solid. E. Okay, what kind of theorem is this? Does it look familiar? Look, divergence is rate of change, right? So it's like the accumulation of flux throughout the interior, calculated by using the rate of change throughout the interior, is equal to the overall flux at the boundary.
So it's just what we did do with extra steps.
But what is that principle, right? Rate of change, like you're accumulating a bunch of somethings using the rate of change throughout the interior. It's equal to the net change on the boundary. Greens also. Yeah, this is another fundamental theorem of calculus. It has the same quality as the others. How many do we have so far? We have the Calc 1 version. Fundamental theorem of line integral. Green's theorem. And so this is what, number 4? It has all the same qualities. The accumulation of a quantity, in this case flux, accumulation of a quantity throughout the interior, and we're going to calculate that flux using the rate of change, right? Is the same as the net change on the boundary, right? The net change of that quantity or the flux over the boundary. That's the same thing, right, as before. This is the rate of change of F. S is the boundary of E. And we're going to accumulate using the rate of change to get the overall or net accumulation on the boundary. Okay, so let's I think we're ready for examples. Yes. So let's do this one first. So here's the one we worked on. And I think we said that for S1, I don't know. But I think that's negative 128 pi over 3. I think this is, we know this is 64 pi. And so then the total flux was?
64 over 3.
I hope. But we're going to find out. So now we have another way to do this problem. How else can we do this problem? Because what am I trying to find? I'm trying to find the surface integral of f dot ds. And I have a solid whose boundary is a closed surface in a vector field. So that's equal to another way to do this now. Triple integral over the solid of divergence of f dv. So we can use the divergence theorem to solve this one as well. So we did the left side, right? We actually found the surface integral for the closed surface S. But because this fits the criteria for the divergence theorem, we've got a smooth continuous solid, a smooth continuous boundary, a smooth continuous field. we can use the divergence theorem. Okay, so we need to calculate the divergence of f. What's that? Our field was y, negative x, z. Divergence is 1, right? 0, 0, 0 plus 0 plus 1. Ooh, that's nice. Right? So, we're going to do the triple integral of 1 dv over e. And how do we want to do that triple integral? What coordinate system should we use here? Yeah, so we're saying polar cylindrical, right? So we want to do, so that'll be what? R dz dr d theta. Is that right? That's dv for cylindrical coordinates. So z goes from what to what? R to 4. The bottom of this thing is the cone, which is equals r. And then r goes from 0 to 4, 0 to 2 pi. See what's happening? Okay, so what is that? ZR antiderivative, so it would be RZ, and then Z goes from 4 to R. So is it R times 4 minus R? Check my math. Antiderivative is Z times R. Z goes from R to 4. So I think that's right. Agree with that? And so then I'm going to have what? 2R squared minus R cubed over 3. And that from 0 to 4. And then all that just times 2 pi. Is that right? So here we go, 2 pi times 432 minus 64 thirds. Check my math, please. 96, so is that 32 thirds? 64 pi over 3? I think it's right. So this is 3. 96 minus 34 is 32 over 3. So I guessed correctly that this turns out to be negative 128 pi over 3 from previous semester. Yes, please.
Could we have just found the volume of the cone and integrated it with respect to z from the bottom up?
You wouldn't even have to integrate, right? What is this integral? So this integral is the integral of E1 dv. So yeah, that's the right. Did you see what happened? We had this integral. What is that? That's just the volume of E, right? That's just the volume of E. With the units of hypervolume, right? So it's the units of hypervolume, but the same value as the volume. So what is the volume of a cone? 1/3 pi r squared h, I believe. So 1/3 pi times r squared is 16 times 4. And lo and behold.
Yes.
So it only worked out that way because the divergence was 1. Because the divergence was 1, then we can interpret that also as the volume of the cone. Okay, so let's confirm the divergence theorem for the cube example, or remember we did a part of the unit cube under that slanted plane? Let's confirm it for the divergence theorem for that one as well. So I think we did, if For that one, I know. We did inward orientation and we got -1. And we said if it were outward orientation, it'd be +1. Remember that? Any questions on this example? So we've actually verified, in doing this problem twice, we verified the divergence theorem for this example. We did the surface integral of the outside surface and got 64 pi over 3. We did the triple integral of the divergence, we got 64 pi over 3. So that, by showing those are equal, that's what's called verifying the theorem. Using the theorem, doing the second half, so using the theorem means you're asked for the surface integral, and so you calculate the other thing instead. That's using the, and then by the theorem you say they're equal, right? So using the theorem to calculate a surface integral of a closed surface means calculating the triple integral of the divergence. That's what using the theorem is. Questions? Okay, so let's do that. We can do it quickly, a lot quicker than doing all 5 sides of the thing. So where was that? This one. So now we're going to use the theorem to calculate this. Just quickly. I think it was that, right? So we're going to do now, we're going to do the triple integral of the divergence of f dv. And we expect to get, what did we expect to get? Do you remember? So that's going to give, that's going to be for outward orientation. Divergence outward is positive. So we're going to expect to get 1. We did inward orientation, got -1. So had we done outward orientation, we would have gotten 1. So when the divergence, we'll calculate outward orientation. So we expect to get 1 for this. What's the divergence of f? Y plus 2y plus 1. Okay? And that's going to be from 0 to, so we'll do dz, dy dx. So z will go from 0 to 1 minus y, and then x and y go 0 to 1, 0 to 1. Here we go. So that's going to be, is that 3y plus 1? Or 3y squared over 2 plus y? No, z. Sorry, respect to z. 3yz plus z. From 0 to 1 minus y. Nope. dy dx. Check my math. So get 3y times 1 minus y plus 1 minus y. And that will give 0. And there'll be integral, double integral from 0 to 1, 0 to 1. So what is all this? 3y minus y, is that 2y? And then minus 3y squared plus 1. With respect to y, we're almost there. Y squared minus y cubed plus 1. That from 0 to 1. And that whole thing times 1, right? So y? Y, yeah, change it. So 1 minus 1 plus 1 equals 1. Got it. So that's doing this problem now using that divergence theorem, right? Rather than calculating the sum of all the surface integrals, do the triple integral over the solid of the divergence. Get the same answer, 1.